This is a video from section 3.3 in a linear algebra class. The directions say to determine whether u and v are orthogonal vectors. Let's take a look at 1a. Suppose we have u equals the vector 6, 1, 4, and v is the vector 2, 0, negative 3. So to determine whether or not u and v are orthogonal, we need to take the dot product of u and v. So the dot product of u and v is 6 times 2 plus 1 times 0 plus 4 times negative 3. And this is equal to 12 minus 12, which is equal to 0. And so notice, the dot product of u and v is 0. And what that tells me is that u and v are orthogonal. So u and v are, in fact, orthogonal vectors. Let's take a look at b. Suppose u is the vector 0, 0, negative 1. V is the vector 1, 1, 1. So if I take the dot product of u and v, this is 0 times 1 plus 0 times 1 plus negative 1 times 1. This is equal to negative 1, which doesn't equal 0. And so, therefore, u and v are not orthogonal vectors. Let's take a look at 1c. Suppose u is the vector 3, negative 2, 1, 3. And v is the vector negative 4, 1, negative 3, 7. So when I take the dot product of two vectors, I like stacking them, one on top of the other. So when I look at the dot product of u and v, I get 3 times negative 4 plus negative 2 times 1 plus 1 times negative 3 plus 3 times 7. Okay. And this is negative 12 minus 2 minus 3 plus 21. And that doesn't equal 0. And so, therefore, u and v are not orthogonal vectors. D. Suppose u is the vector 5, negative 4, 0, 3. And v is the vector negative 4, 1, negative 3, 7. Okay? And let's take the dot product of u and v. Well, that's 5 times negative 4 plus negative 4 times 1 plus 0 times negative 3 plus 3 times 7. So this is negative 20 minus 4 plus 21. That doesn't equal 0. And And so that's fine. Yeah, u and v are not orthogonal vectors. And that's how you do problem 1. Now, so the directions say to find a point normal form of the equation of the plane passing through P and having n, the vector n, as a normal. And with that, let's take a look at 3. Suppose my point is -1, 3, -2. And my normal is -2, 1, -1. So how does this work? Okay, so I'm going to take -2, right? That's the first component of the normal. And I'm going to multiply by x minus -1. Then I'm going to go plus 1 multiplied by y minus 3 minus 1, right? That's the third component of the normal. And then I multiply by z minus -2. And I'm going to set this equal to 0. And so going a little bit further, this is -2 times x plus 1 plus y minus 3 minus, well, I'll just say minus, and then in parentheses, z plus 2 equals 0. And then, in fact, for a fact, I'm going to leave the 1 out in front so we see it a little easier, because I want to emphasize what the normal to that plane looks like. So I'm going to put the 1 here times y minus 3, and then minus 1 times z plus 2. And that's called the point normal form of the equation of a plane. Let's take a look at 4. Suppose we have the point 1, 1, 4. And then my normal is the vector 1, 9, 8. So I take the first component of the normal and then I multiply by x minus 1. Take the second component of the normal, multiply by y minus 1, right? And then take the third component of the normal and multiply by z minus 4. And then I'm going to set this equal to 0. And then that's my point normal form for the equation of a plane. Number 5. Suppose P is the point 2, 0, 0. My normal is the vector 0, 0, 2. So I'm going to take 0, that's the first component of the normal, times x minus 2 plus 0 times y minus 0 plus 2 times z minus 0. And then I'm going to set this equal to 0. And so, therefore, the equation is 2z equals 0. And then that's how you do 5. On number 6, suppose we have the point 0, 0, 0, and then my normal is 1, 2, 3. So I'm going to take 1 times x minus 0 plus 2 times y minus 0 plus 3 times z minus 0 and set that equal to 0. And so therefore 1x plus 2y plus 3z equals 0. And that's how we do 6. Over here, the directions say to determine whether the given planes are parallel or parallel. So determine whether the given planes are parallel. To determine whether the given planes are parallel, we look at the normals. So, for example, if we take a look at 7, I have the plane 4x minus y plus 2z equal 5. And then I have 7x minus 3y plus 4z equal 8. Now, n1, right, is equal to the vector 4, negative 1, 2. And then that's for the first plane. N2 is the vector 7, negative 3, 4. Now, notice, we cannot write n1 as a scalar multiple of n2. So that's what that says is n1 is not parallel to n2. And if the normal vectors are not parallel, what that tells me is that the planes cannot be parallel either. So it's just really nice to look at the normal vectors. Let's take a look at number 8. Suppose x minus 4y minus 3z minus 2 equals 0. And then we have 3x minus 12y minus 9z minus 7 equals 0. Now, n1 is the vector 1, negative 4, negative 3. n2 is the vector 3, negative 12, negative 9. Okay? Now, notice, n2 is equal to 3 times n1, right? And so therefore, n1 is parallel to n2. And if the normal vectors are parallel, that implies the planes are parallel. I hope that makes sense, or that's reasonable. Let me give you a picture of this, right? So if this is the vector n1, right? And I'm going to give you kind of a two-dimensional visual of this. Suppose this is the plane, right, that n1 is parallel to. So we'll call this plane 1. Now we have another vector n2 over here. And suppose this is the plane that n2 is parallel to. And we'll call this plane 2. Can we agree that if n1 and n2 are parallel, the planes are forced into being parallel? If n1 and n2 are not parallel, there's no chance that these planes are parallel. Because by design, plane 1 has to be parallel to n1, and plane 2 has to be parallel to, plane 1 has to be perpendicular to n1, and plane 2 has to be perpendicular to n2. And so if they are not perpendicular, those planes are not going to be parallel to each other. Now, let's take a look at this one. Suppose I ask you, determine whether the given planes are perpendicular. So again, we can look at the normals. If the normals are perpendicular, the planes have to be perpendicular. Now, suppose we have 3x minus y plus z minus 4 equals 0. And then we have 1x plus 0y plus 2z equals negative 1. So n1 is the vector 3, negative 1, 1. N2 is the vector 1, 0, 2. So if I take n1 and dot it with n2, what do I get? I get 3 times 1 plus 1 times 2. That's not 0. So n1 and n2 are not perpendicular. They can't be. And so therefore, the planes are not perpendicular as well. And that's how we do 11. So let's take a look at this. Suppose I ask you, find the distance between the point and the line. This one's good. So we're going to take a look at 21. So the point is negative 3, 1. The line is 4x plus 3y plus 4 equals 0. Now, the distance, I'm going to call D, is, I'm going to take the absolute value of my A is the coefficient of x. So I'm going to take 4 times this, it's the first coordinate of the point. So 4 times negative 3. I'm going to go plus, then I'm going to take 3, and then I'm going to multiply by the second coordinate of the point, 1. Then I'm going to add 4. And remember, it's a distance, so this is an absolute value. I'm going to divide by the square root of a squared plus b squared. So it's the square root of 4 squared plus 3 squared. Now, here, negative 12 plus 7 is negative 5. The absolute value of negative 5 is 5. So this is 5 divided by 5, right? The square root of 4 squared plus 3 squared is the square root of 25, which is 5. And so this distance is 1. Let's take a look at 22. Suppose we have the point negative 1, 4, and then the equation of the line is given by 1x minus 3y plus 2 equals 0. Now, D is the absolute value. I'm going to take 1, that's the coefficient of x, times negative 1. Then I'm going to go plus negative 3 times 4. Okay, that's where I'm getting the 4. It's the second coordinate of that point. And then I add c, and then I'm dividing by the square root of negative 1 squared plus 4 squared. Plus, let me back up. My a is 1, right? So it's the square root of 1 squared plus negative 3 squared. It's the square root of a squared plus b squared. That's where I'm getting that denominator from. Now, negative 1 minus 12 is negative 13. Negative 13 plus 2 is negative 11. The absolute value of negative 11 is 11. And then I'm going to divide by the square root of 10. Now, if I rationalize that denominator, right, I'm going to multiply numerator and denominator by square root of 10. And when I do that, the distance is 11 times the square root of 10 divided by 10. That's how we do 22. Now, let's take a look at 23. Suppose we have the point 2, negative 5, and the equation of the line is y equals negative 4x plus 2. We have to be careful because to apply the distance formula, the equation has to be of the form, the equation of the line has to be of the form ax plus by plus c equals 0. So when I fix this, it's going to be 4x plus y minus 2 equals 0. Okay, so here's my a, the 1 is my b, and my c is negative 2. So d, it's the absolute value of 4 times 2 plus 1 times negative 5 plus a negative 2, that's all an absolute value, divided by the square root of 4 squared plus 1 squared. 8 minus 5 is 3. 3 minus 2 is 1. This is 1 over the square root of 17. So if I rationalize this denominator, I multiply numerator and denominator by square root of 17. And then when I go to finish, d is the square root of 17 divided by 17. And let's take a look at 24. Suppose I have the point 1,8, and the equation of the line should be written in the form 3x plus y minus 5 equals 0. Your distance will be affected. You won't get the correct distance if it's not written in this form. So d is the absolute value of 3 times 1 plus 1 times 8 minus 5, divided by the square root of 3 squared plus 1 squared. So 3 plus 8 is 11. 11 minus 5 is 6. Absolute value of 6 is 6. And then I'm going to divide by square root of 10. Multiply numerator and denominator by square root of 10. And so, therefore, d is 6 square root of 10 divided by 10, which is 3 root 10 divided by 5. And that's a good stopping point for this video. This is a video from section 3.3, and we looked at problems 1, 3, 4, 5, 6, 7, 8, 11, 21, 22, 23, and 24. Okay, thank you.